Good morning. Welcome back to 2341, our 8 a.m. class here on Tuesday, Thursday. It's Thursday after our what snowpocalypse, ice disaster the day after tomorrow. I've heard many things. So I hope all of you have fared well and all of your families have fared well as well, or at least starting to recover from that. Thank you for coming back and spending some time with me while I talk about organic chemistry. So one of the things I want to make sure we say is that, it's been a really hard semester. And so if you need help, go ahead and reach out to a friend or a family member or the student services here on campus. If you need just a little extra, that was a little extra more stress than I was hoping for on this last thing. And so I reached out and got some help myself. And so I encourage you to do that if you need that kind of help. Okay, so that being said, let's get back to the task at hand, which is our exam next Tuesday. Okay, and I will be emailing out that, actually I'm gonna email it out Monday, all the instructions for it, because we don't come to Zoom, you go directly to Top Hat. Make sure you go ahead and go download the Proctorio plugin for Google Chrome on your device to take the exam. Okay, that is a requirement for the exam. And then what's going to happen is it's going to talk you through it after you log in. It'll give you a choice of exam A, B, C, or D, depending on whether you have ODS accommodations or which randomly assigned exam you got. It will ask you to go ahead and log in with your camera on. It doesn't record audio because that tends to kick people out a lot with like dogs barking in the background, but it does record everything else, and your screen changes and all that. It's going to ask you to kind of go scan your room, make sure there's nobody there or another computer that you can hack on while the exam is going on. And it records the entire session, and nobody's watching, okay? It's completely AI. And then when the exam is over, it gives me a list of things like, oh, these people had anomalies in there or have a suspicious activity in there. And then I personally review them, look at, a lot of the times it's just the cat jumping on the keyboard. So most of the time it's not a big problem. But I want you to know it's going to be a lot less stressful than an examity exam where somebody's yelling at you all the time. So this is going to be completely your computer. And then if something looks suspicious, I review it. And then if there is something suspicious, we'll have a talk. If there's nothing suspicious, then we'll just go ahead and continue on. Also, there are 120 points available on this exam. There's 30 questions. You'll have the entire class time to take it, longer if you have ODS accommodations. And when you do this, don't look at that raw score as, oh my gosh, I got a 75 out of 120. That doesn't mean you got a C or an F or anything, because what I do is I look at how the class did as a whole, and then I can move the average around. I try to get an average around 75 on the exam there. So don't look at that raw score and say, oh my gosh, I did very badly. No, the group activity is not due today because we haven't actually done that. There should have gotten a new schedule of when our new group activities are. I sent that out on Monday. We're having to truncate our schedule there. And so I'm actually going to a workshop on Friday to see about other ways to make sure we get all of our information in without being overloaded. Okay, so the group activity won't be until after we start chirality, and that's the chirality group activity that'll be due next week. Actually, it won't be due the following week, because we'll start chirality and then we'll do that group activity. Okay, so you'll notice also in the email I sent out Monday, all of your homework is due on Friday. The reason it's due on Friday is so that after Friday at midnight, you can now use all that homework for review, okay? All that homework opens up, it tells you what the correct answers are, and you can use that as a review to help you study for the exam over the weekend and on Monday, or Monday morning, if Monday at midnight, whenever you start to study for the exam. And you can use that to help you with that. The other thing I'm going to do is I'm going to go through the review slides I have today. And these are also already posted on Canvas. I want to hit some highlights, concepts you must understand and be able to apply. So what you can do is go through the exam review and say, okay, none of that looks familiar at all. I have a lot of studying to do. Or only these 3 slides don't look familiar. I'm going to study those things first. Then I'm going to go to the homework and look at the homework and say, hey, you know, did I answer it right? Yes. Okay. Did I answer it right for the right reason? Remember, there's comments on why, discussions about why it's the right answer or the wrong answer. So you look at that, and if you got it right for the right reason, go ahead. All right, you've got that topic, move on to the next topic and continue on like that. I think studying like that will give you an opportunity to kind of reinforce what you do know and kind of give you a hint of what you don't know. And so what you need to kind of focus on, okay? So with that, are there any questions about the exam, the process of the exam, before I go into the review?
Did you say that you're going to like mail out instructions for it too?
Correct. I'm going to actually mail it's going to go out at 6:01 a.m. on Monday morning. And basically it's something like you must have Proctorio installed. Top Hat suggests you actually shut your computer down, reboot it, because that, you know, it'll take any cache hogs off of your computer. Only open Google Chrome and only open Top Hat. That'll save you a lot of trouble with it trying to kick you out because there's too many windows open. And then go ahead and, you know, log in instructions, having a picture ID, student ID, or your driver's license is fine. Again, it's on AI. It's not going to be, you know, some other person looking at your ID and stealing your information. I'm the only one who will ever see it. Let's see. And then you can have 2 pages of scratch paper. And that doesn't kick out the AI if you're using it in front of you to use a scratch paper. You just have to show it to me at the end of the class, showing that you didn't just copy down all the answers to help someone else. Okay. All right. And so those are the kind of instructions you'll get on Monday. Okay.
Thank you.
And for style of question, I'm using the exact same style of question as what's in the homework. So the way it's asked, the multiple choice type stuff, the matching and stuff, it's all very similar to the homework. In fact, it would be, you know, almost the same words, but different structures or different, you know, is this more electronegative or less electronegative? So look for that as the style of question and get comfortable with that style of question. Okay. All right. So for our review, I'm going to go ahead and start sharing my screen with my iPad. And all right, I'm going to have to move my participants up over here because, all right, putting the gallery view up here so I can see who's drinking coffee. And put that over there, and I'm going to keep that there. All right. All right, can you still see my exam 1 review slide? Sometimes when I move it, it blinks out. All right, so thank you. All right, so what I want to do here is I'm going to talk about the topics, and we're going to start with chapter 1 and go all the way through chapter 4. And I'm going to draw some connections between the different chapters too. So those might be things you want to write down. But the idea here is to get familiar with the material and make sure that we're looking at it in the right way. Okay. So the first thing we have to think about is, what are bonds? Well, bonds are electrons, so we have to know where the electrons are. So that starts out with this idea that we're going to fill our energy levels from the bottom up. And when we do that, we're going to always fill our 1s first. And then most of the time, we're dealing with these 2 level 2 principal energy levels, because those are the ones that are found for carbon, nitrogen, oxygen, fluorine. Okay, so most of the time we'll be dealing with those. When we go up to other elements like sulfur and phosphorus, we're going to end up using these up here. But for most of the time, that S and P orbitals in that number 2 energy level is what we deal with. And so we need to know how many electrons are in that level, because those are our valence electrons, and the valence electrons are the ones that bond. Okay. So do you have to memorize them? No, there's a periodic table at the beginning and end of the exam, so you can scroll either way. And you can use that periodic table to tell you how many valence electrons you have. Because by knowing, it's not this periodic table, by the way, it's just a regular periodic table. You have to know where the S's are. If you know the 1s is right here and the 2s is here, and then the two P's are here, then you'll be able to see how many valence electrons you have. The number of valence electrons is equal to the column number. So if you're in column number 1, you have 1 valence electron. If you're in column number 6, you have 6 valence electrons. So you can always find the number of electrons just by looking at the periodic table. Okay, so again, don't memorize, just know the trends that you can see from the periodic table. All right. The next thing we need to talk about is electronegativity. Electronegativity is very important, okay? It tells us whether or not our bonds are polar or not. It tells us whether we're more likely to have an ionic bond or a covalent bond. So this is very important. Again, you don't need to know the actual numbers. I have a question here. Can you use a printed periodic table during the exam? No, I would prefer you use the one on there because everybody would have the exact same one. Okay, you can use blank pieces of paper, but I want you to use the periodic table that's in the exam. Okay.
I have a question, Dr. Irvin, about this electronegativity chart. So whenever there was like a slide that had like non-polar, polar, like ionic, and it was like greater, less than, or whatever, and the difference between. So are there going to be questions like that then on the test, so that we are going to have to know?
No. I believe that you need to know whether something is a polar or non-polar. It's going to be something very specific, like, is the carbon-fluorine bond more polar than a carbon-nitrogen bond? Okay, and you can tell that just from the trend, because carbon and nitrogen are much closer together on the table, so it's going to be a less polar bond than the carbon-fluorine bond. Okay, so you need to draw those kind of conclusions from electronegativity. Okay?
Thank you.
Okay. Now, knowing the trend here, that fluorine is, of course, the highest electronegative atom. It's a very small ion, holds those electrons really, really close to the core, and that's why it likes to have those electrons there. And then it goes down as we go down rows, and it goes down as we go down columns. So if you start along here, you know that the, carbon is going to be less electronegative than nitrogen, which is less electronegative than oxygen, okay? And so we can draw those simple trends just by looking at their position on the periodic table. Know this trend, that's the most important part of this, okay?
I have a question.
Yes.
When I was doing the acid-base stuff yesterday, I couldn't figure out, is fluorine a stronger electron drawing group or a nitro group?
The nitro is actually a stronger electron withdrawing group because the nitrogen that's directly bound to the carbon there has a full positive charge on it.
Okay.
If you looked at the formal charge, fluorine just is inductively electron withdrawing. It's pulling electron density through the bond, but nitrogen actually has a full positive charge on it, and that makes it more electron withdrawing.
Okay, thanks.
Okay. So good question though. And that I'll bring up something later, actually. So knowing that bond polarity is associated with that difference in electronegativity is important, and knowing that general trend, because we have the bonds we deal with mostly are these non-polar bonds, like this fluorine-fluorine bond or a carbon-carbon bond. And those tend to be less reactive because those are non-polar bonds. There's no real way to attack one or the other. What we want to do is look at those things that have polar bonds, because polar bonds is where we can now have attack by other species. That's where the reactions are going to happen. And so when we get into the next chapter 6, we're going to see that we're looking for that most polar bond. It's probably going to be the one that's going to react. And it's going to react in a specific way based on this polarity. So knowing the concept of bond polarity is very important. Okay. And again, the general trends of electronegativity gives you a relative idea on whether they're more or less polar. Okay. All right, which brings us up to Lewis dot structures, okay? Lewis dot structures, being able to draw them correctly with all the correct number of electrons is very important, okay? Including calculating out the formal charge, okay? Calculating out the formal charge will tell you a lot about the atom, okay? Remember, when you do your Lewis dot structures, you get all your valence electrons, put your less electronegative atom in the middle, and then you build out from there. Hydrogens only bond ones, halogens only bond ones. Use all those rules to build these. And yes, you can have positive charges, and you need to indicate if you have a positive charge on that atom, okay? We can even, in chapter 10, we're actually going to do things where we have radicals, unpaired electrons. And so that's going to give us some interesting stuff to do there. And then we can, of course, have neutral stuff, even though they don't fill an octet, like boron here. It still gives us a neutral one that has a formal charge of 0, and therefore it's a neutral atom. Notice that you must also add the lone pairs whenever you do a Lewis dot structure. You need to remember that those lone pairs are there because it changes the molecular geometry. So you need to make sure you always draw your lone pairs. And of course, if you have an excess of electrons more than protons, then you end up with a negatively charged species, and you need to indicate that. Notice most of the time the negative charge is on a lone pair or an atom that did not fill its octet until making that 4th bond. Okay. All right. Questions on Lewis dot structures. And they're kind of simple, but they tell us so much. Having a valid Lewis dot structure will give you a lot of information. Okay. All right. So hybridization is the next big one. Okay. So I just saw a really cool video on hybridization on YouTube, and I'm gonna put a link to it in the announcements on our page. It actually does a very good job at visualizing it. I hope I did a good job at visualizing, but if you still don't get it, I think I'll post that there and you can go look at that. So we know hybridization happens because if we tried to bond the electrons where we filled them up first, like here, we would not get the molecular geometries we have. So there must have been something different. Okay. So by losing a little bit of energy in the P and raising the energy of the S and blending them together, we get that hybridization. And when we have all 4 of those orbitals shared together, we have that sp3. Okay. When we have one of the P's left over, we can form a pi bond, and we have a different molecular geometry. Okay. So hybridization tells us something about the molecular geometry as well. And then in our last one, where we only have one p orbital shared with the s, we have a linear molecule, and we have the ability to make 2 pi bonds. Okay. Now, we also need to think about the amount of S character in these, because it controls several things. Number 1, it controls bond strength. Number 2, it'll control the acidity of a compound. And number 3, it will control the bond length and or frequency that we see in IR. So knowing this is actually important in 3 different aspects. Okay, so why is S character so important, right? S is the small sphere where the P's are sticking out away from it, right? So if the S is small, really held in tight to the nucleus, those electrons are held tighter and therefore are more likely to stay there than the ones in the P's, because the P's are further away, have less pull by the nucleus, right? So that means that the more S character you have, the shorter, stronger bond you have, okay? So shorter, stronger bond, or the more ability to stabilize a negative charge. Okay, so let's talk about shorter, stronger. Okay, so if we look at the bond lengths between the hydrogens on all of these molecules here, right here, these are longer than these, which are longer than these. Okay, now when we talk about IR, these are at a lower frequency than these and these and these. These are at the highest frequency at 3,300. These are just below 3,000, right? So the hybridization changes our frequency because it changes bond strength. Okay, so now let's compare that with acidity, right? If this carbon here has more S character, those electrons are held tighter to that carbon, and therefore it's more likely to stabilize a negative charge. It's smaller in size, and it's more likely to stabilize a negative charge. That means that the acetylene is going to be more acidic, that proton, than the ethylene, which is more acidic than the ones on methyl groups. So this combination of S character does those three things for us, okay? Gives us bond lengths and strengths, gives us frequencies in IR, and gives us acidity. All right, questions on hybridization?
Could you repeat its relevance to acidity?
Acidity, okay. So when you have in the case of SP, it's half S, half P, right? So those electrons are held tighter to the core, to the nucleus, because the s orbital is much smaller than a p orbital. And so it's going to have more, it's going to be closer to the nucleus. If it's closer to the nucleus, it can more easily stabilize a negative charge because it's held tightly to the counterbalancing protons in the nucleus. Therefore, the more S character you have, the more stable that ion is, which means the more acidic the hydrogen is. It's easier for that hydrogen to leave because the ion left behind is more stable. Okay, does that clear it up?
Yes.
Okay, so, you know, I wanted to draw some attention to that S character. We talked about it in 3 different chapters in 3 different ways. So I wanted to draw your attention to it. It's all related to that concept, okay? All right. Any other questions on hybridization? Okay. So molecular shape, how many bonds you can form, whether you have sigma or pi's, it's all related to hybridization. All right, and molecular structure. So this is where a valid Lewis dot structure and knowing your hybridization comes in, because the electronic structure is where you can have your lone pairs, okay? And if the lone pairs are taking up space, that changes your molecular geometry. So knowing your hybridization and number of lone pairs tells you your geometry. For example, right here in sp2, if you have 3 things attached to it, this means bonds, ligands means bonded to, and you have no lone pairs, you have a trigonal planar 120 degrees apart. But if you have 1 lone pair, you end up with a bent molecule, okay? It's not the same bent as this molecule here, because this is closer to 120 because the lone pair is that 3rd one. And again, when we go to 2 things bonded in our tetrahedral shape, we have 2 sets of lone pairs, okay? So that's why drawing those lone pairs is important. Questions on molecular versus electronic geometry? Okay. So once you get your Lewis valid dot structure by knowing how many valence electrons you have, sprinkle the atoms around, throw in your lone pairs, you have a lot of information about the reactivity of that molecule. Okay, so this brings us to our specific intermolecular forces. The 3 most important are hydrogen bonding, dipole-dipole, and induced dipole-induced dipole. We rarely use ion-ion in organic chemistry. We do use ion dipole sometimes to help make reagents happen in the solution. However, hydrogen bonding is very important. You have to have a hydrogen that is bonded to an electronegative atom, and it has to have some lone pairs for that hydrogen to bond to. Dipole-dipole means that you don't have a hydrogen, you have a polar bond, okay, like a carbonyl, where you have a partially positive side and a partially negative side. And your induced dipole is when you don't have any of these things. Think carbon-hydrogen bonds only. And the only way they can do it is to induce a mild force there to get them to kind of stack together for a short period of time. And then when they move away, the induced dipole goes away as well. Now, hydrogen bonds are much stronger than dipole-dipole, and dipole-dipole is much stronger than London forces. So that means that hydrogen bonding affects your solubility, it affects your boiling points. So things that hydrogen bond tend to have higher boiling points than things that just have dipole-dipole. And things with London dispersion forces have lower boiling points, assuming we have all the same molecular weight. Remember, as molecular weight goes up from methane to ethane to butane, the boiling point does go up just from the sense of the mass, but by adding additional intermolecular forces, you can increase that even more. Questions about specific intramolecular forces? And notice these interactions also do with solubility and miscibility, so like dissolves like, etc. Okay.
I remember you saying something about sulfur can also hydrogen bond. I've never seen that anywhere before.
Oh, it actually doesn't hydrogen bond very well at all, because the electronegativity between sulfur and hydrogen is actually very low. It's almost the same as carbon hydrogen, so it doesn't hydrogen bond. Oxygen Here, something needs in. Oxygen and nitrogen.
Oh, I thought I remember you.
Oh, it can slightly, but it's the weakest hydrogen bond available.
Oh, okay.
Oxygen is much stronger than nitrogen, and nitrogen is much stronger than sulfur. Okay, so, and it all has to do with the difference in the electronegativities between the oxygen and the, and technically the hydrogen in HF can also hydrogen bond because it has a polar bond as well. Okay. And by the time we get to carbon, they're so close together that that carbon and hydrogen doesn't hydrogen bond because it's not a polar enough bond. Okay?
Yes, thank you.
All right. So the last thing I wanted to talk about is resonance structures. And because we use them, and when we use these resonance structures, we can tell a lot about the characteristics of the ion form. And it starts with that valid Lewis-Dot structure. And then we go ahead and we calculate our formal charges. And when we have these equivalent resonance structures, we can see that why this molecule is actually so stable, because instead of having the negative charge on one atom only, like in this structure, or one atom only, like in this structure, it actually can be spread out over all of these oxygens, making each one have 2/3 of a negative charge on there. And 2/3 of a negative charge is easier to stabilize than a whole negative charge. So we have 2 negative charges, we have 3 atoms. So we have spreading 2 negative charges out over 3 atoms. So each of those atoms only carries 2/3 of a negative charge. And that's why equivalent resonance structures are important, especially in the acetate ion. And this is how we can help look at stabilizing that charge over an area. In fact, the acetate ion, it's almost a half. It's 1/2 because it's 1 negative charge spread out over 2 oxygens. And that's another reason the acetic acid is the most acidic organic compound that we play with. All right, questions on resonance structures. Okay. All right, so that brings us on to chapter 2, okay? Now, we learned about all the different functional groups we're gonna learn in organic chemistry. We learned how to name them, and then we learned priority. Of course, in this class, we're only going to get up to probably aldehydes and ketones because we introduced them at the alcohol chapter. But we need to know this for the follow-on semester. So knowing what the functional groups look like, you know, knowing that, oh, it's carboxylic acid because it looks like this general structure. Remember, R could be anything. It can be a long chain, it can be a ring or whatever, it doesn't matter. The R is just whatever. The important part is the part in red. That's the distinguishing feature of that functional group, okay? And notice all of these right here are all carboxylic acid derivatives. They're all just different kinds of carboxylic acid derivatives, so they're all closely related. But then we also have our nitrogen amines, and this is actually a carboxylic acid derivative as well. So know that priority, that when you have a hydrocarbon, it's named for the hydrocarbon, and then the first functional group to change your name is the amine. And then you can go up from there with the thiol, the alcohol, ketone, and aldehyde, etc. Okay, so the functional groups are important because when we also talked about IR spectroscopy, we talked about how different types of bonds absorb in different places. Okay, now, when different types of bond absorbs in different places, you can look at it and say, oh, on this zone here, I have an oxygen-hydrogen bond. On this zone here, I have a carbon-carbon double bond. On this zone here, I have a carbon-oxygen double bond. I can start building what possibly could be my thing based on what is there, okay? Now, let's say I give you an IR spectrum and I give you 3 choices and only one of them has a carbonyl. And in your spectrum, you have a strong absorbance in that 1700 to 1800 range, okay? You're gonna be able to immediately say, okay, none of these other structures have a carbonyl, but that is in the carbonyl zone, that is in the carbon-oxygen double bond zone. And so you will be able to pick it out from that. So that's one of the real reasons to look at these functional groups and try to get these in your head and organized. Okay, now the next thing we do is nomenclature. Now there is a document on Canvas that has every single rule for doing this in order, okay? And then you can use these rules. If you use them in order every time, just use the rules until you're done. You don't have to use every rule if you don't have E and Z, if you don't have cis and trans. You don't need to go down any further. Start at the top and move down until you're done, okay? But don't forget to use the different functional group names that we have, alcohols, etc. All right, so the first and most important rule is to identify that principal group, because that's going to name your compound. Everything else is a substituent, okay? So you can look at any chemical compound. In fact, I just got my son's prescription out and folded out that piece of tissue paper that's about that big when you fold it out, and started reading the name of the compound itself. And, you know, because I'm a geek and that's what I do, but it was, I could actually go, I went all the way to the end and said, oh, it's, you know, this is a carboxylic acid derivative. And then I looked at the infix and I saw that, oh, it has an alkene in it. Then I looked at the prefix and the parent was a deca. So I knew that that was the core of the molecule. And then everything else was a substituent, okay? And of course, there's numbers and locations for each of those substituents. So we can know exactly how to draw that compound with just looking at the idea that you have the substituents, which are everything before the prefix. The prefix is, you know, metha, etha, deca, penta. And then our infix is the ane, ene, and ine. If you have a single bond, double bond, triple bond, okay? Suffix tells you the functional group. If it has an all at the end, that's an alcohol. If it has an al at the end, it's an aldehyde, okay? So you can break any chemical name down into the structure. And the other thing you can do is by looking at this name, you can start building up the compound from the different parts. Start at the end, look at the infix, look at the prefix, and then you should be able to add all the substituents on from there, okay? So there, you might, I think there's some homework there that you got to pick the compound from the name or pick the name from the compound. And so that you can, you know, practice that, kind of go back and forth. Look at a compound, try to make the name, look at the name, try to make the compound. And we did that in class thing for that as well. All right. This I add as a special thing because we use this group a lot. It's called the acetyl group. It's the carbonyl with a CH3 on it, okay? This right here is the acetyl group. And it's named so many different things, we have to kind of call it out. And so it's acetic acid, acid amide, acid aldehyde, acetone, and acetic anhydride. So this acetyl group we're going to use a lot in our chemistry, especially when we get to the alcohol's functionality. So I wanted to call it out as a special thing because its nomenclature is related to that we use this compound so much. Okay, so questions about nomenclature? All right, I forgot to put a slide in here about IR. Okay, in the IR chapter, in the slides, there's that one slide that shows you where all the different types of bonds are. Knowing the zones where all those bonds are is very important, okay? So knowing that the high end, you know, just below 3000 is where you find the sp3 hybridized carbon hydrogens. And knowing where the sp2 hybridized hydrogens are just above the 3000 mark, and knowing that SPs are above it at a 3300. Knowing that your oxygen hydrogen bond is up there, knowing that your nitrogen hydrogen bond is up there is important. Then our next thing is our triple bonds, our cyanos and our acetylenes. Those are in that 2200 range, knowing that those are the only thing there. So those are going to be their triple bonds, your strongest bonds. And then you move down into that 1600 to 1800. That's where we have our carbon-carbon double bond and our all-important carbonyl, our carbon-oxygen double bond. Carbon-nitrogen double bond also shows up there, but we don't see it very much. Then the lower one, we have a very strong carbon-oxygen bond Usually the carbon-carbon bonds are a little weak, the single bonds that are down in that 1500 and below. And of course, knowing that you can build those different fragments, knowing that if it's absorbing there, that fragment must be in the IR. So you have to include that fragment that's absorbing in whatever structure you're trying to pick from, okay? So I would definitely study that chart and get those kind of things in order. Okay.
Posted, by the way?
Huh?
Is this exam review posted?
Yes, it's on Canvas. It's called Exam 1 Hot Topics.
I have a question about the nomenclature.
Yes.
So for the trans, the cis, the E, and the Z, that's when you're using double bonds and triple bonds, either separately or together.
Mm.
But I've been noticing that on some like practice questions on the homework, there are questions that have the double bonds and the triple bonds, but they don't require you to add the trans and the cis. So how do you know when to add?
Okay, triple bonds don't have cis or trans, and so because they're linear, but double bonds do have cis, trans, E, or Z. And the rule of thumb is if you only have 2 groups, you can use cis and trans. If you have more than that, you should use E and Z. What I would do is I would look at the answers, and if there are E and Z in the answers, then you should probably assign those E and Z. Okay. Most of the time, what you might actually see is you might see something that has a double bond in it, and there's no E and Z assigned because let's say you have 2 methyl groups on one of the ethylene carbons. There's no way to assign priority. And so you can have 3 methyl groups on ethylene, and it can't be E or Z because there's no way to assign priority. And so you might see that sometimes. Okay?
Thank you.
Yes, the test is going to be 30 questions, multiple choice on top hat. All right. All right, so let's go to acids and bases. Okay, the most important definition here is a Lewis acid is a substance that can accept a pair of electrons, okay, to form a new sigma bond. Okay, write that down, form a new sigma bond. A Lewis base is a substance that uses a pair of electrons it already has to make a new sigma bond. Excuse me. Okay, let's think about that. So how can we correlate this to Bronsted-Lowry? Okay, the hydrogen is accepting a pair of electrons from something else to make a new sigma bond. Therefore, the hydrogen is a Lewis acid. Okay, the Lewis base is whatever had those electrons that reached out and grabbed that hydrogen. Okay, so this definition also follows for Bronsted-Lowry. Okay, so this is the broadest definition of acid and bases, and it's the one we're going to use the most. So knowing this is very important. Okay, notice with this, you can do it to form a charged species, and then it's going to have some kind of equilibrium going from back and forth. But notice that these electrons were the ones that came out, created a new sigma bond in between that boron and that oxygen to create that new compound. Okay. It's a charged species, but you know, it's balanced, counterbalanced. So the net charge on the molecule is 0. Okay.
Can you tell us the formula for formal charge again?
Formal charge, okay, formal charge is equal to the number of valence electrons, okay, bracket, 1/2 of the bonding electrons plus, okay, wait, hold on. Number of valence electrons minus bracket 1/2 of the bonding electrons plus the non-bonding electrons. So all of the electrons on the lone pairs plus the 1/2 of the bonding electrons in brackets. Do that math first, minus the number of valence electrons. Okay?
Thank you.
Okay, so notice that when we do this other reaction here, we start with an ion species, we attack one here, and we kick out another ionic species here. Okay, so it's the same thing. Those electrons are being used to create a new bond. These electrons have to go away because we can't bond 5 things to carbon. So we have to have that leaving group available to us. And we're going to talk a lot more about that in chapter 6. Okay. So let's go and talk about Bronsted-Lowry a little bit, because that's also very important in the fact that we need to know Bronsted-Lowry and we need to know pKa's to determine which way the equilibrium of the reaction lies, okay? One way to look for it is the stronger base always wins, okay? Meaning the strongest acid is always converted to the weaker acid, okay? Let's see, there's also the condensed valence electrons, equal bonds. Oh, that's cool. There's another way to remember that if you want to use that one as well. Number of bonds and number of dots, but that's kind of cool. All right. All right. So the strongest base always wins, or the strongest acid is always converted to the weaker acid. Okay. So what you're looking for is in your pKa's, when you try to figure out which way this is going to lie, you figure out what's the acid on one side of the reaction, what the conjugate acid is on the other side of the reaction, and compare the pKa's. Okay. And remember, the more negative, or the lower the number and or negative the number, the stronger the acid. So 0 and below are all of our strong acids. As we go up from there, they get to be weaker and weaker acids. Okay, so you're looking for the higher pKa number, and your equilibrium is going to be shifted in that direction. Okay, so I told you there's a few you need to remember. This is the ones you need to remember. Okay, because we are going to use them so much, we really want to kind of take that into account. We want to think like things like HBr and hydronium ion are very strong acids. Yes. Yeah, there's some more comments in the chat there. Then the next most important one here is the acetate ion, the acetic acid here. It's right around 5. I'm adding this one because we're going to use it a couple times here. The phenol is because we learned that it was more acidic because of the ability to draw resonance structures. That a phenol is more acidic than a regular alcohol because we could share those electrons. And so that's one of those important factors that controls acidity. Okay. All right, and then of course, water and alcohol are about the same, right around 15, 16. And then the acidity of these right here. We talked about this in chapter 1, where the acidity of these are controlled by the S character. The acetylene has most S character. It has 50% S character, and therefore it's the most acidic. This has 33% S character, so that's the next most acidic. And this has 25% S character. It's the least acidic, okay? So hybridization controls the acidity of those carbon and hydrogen bonds, okay? So, but yeah, the ones in orange plus that phenol, I think, are the most important ones to, you know, have a good idea about where they are. There we go. All right. There are 4 factors that makes one acid more acidic than the other, okay? So the first thing we look at is electronegativity and size, okay? So if you're moving down a row where the electronegativity is changing, but the size is not changing, the more electronegative atom is going to have a more acidic hydrogen. So the hydrogen on fluorine is more acidic than the hydrogen on oxygen, which is more acidic than the hydrogen on nitrogen, okay? So if we're moving down a row, electronegativity determines it, okay? However, if we're going down a column, size determines it, okay? Fluorine is very small and it has to hold that charge over a very small sphere. Chlorine is much bigger and it's easier to hold that charge, meaning the hydrogen on chlorine is more acidic than the hydrogen on fluorine. So down a row, electronegativity dominates. Down a column, size dominates. Okay. Now, resonance and delocalization also helps. The more you can spread charge out over a greater number of atoms, the more likely it is to lose that hydrogen. Think the acetate ion versus ethanol, right? Ethanol, when it loses its proton, that charge stays on the oxygen. When you look at the acetic acid, you can spread it out over 2 oxygens. And that's why it has 10 points, 11 points of pKa's stronger than the ethanol because of that delocalization. The next thing we have is the inductive effect. Okay, resonance spreads the charge out over different atoms. Inductive effects actually pulls electrons through the bonds. Okay, it's not directly bonded to the hydrogen, but it pulls electron density through bonds adjacent to that acidic hydrogen. And then of course, the last thing that changes is hybridization. Okay, and hybridization is not just for those carbon atoms, it's also for nitrogen atoms and oxygen atoms. We can see sp2 hybridization and sp3 hybridization in nitrogen and oxygen as well. Okay, questions on that? All right. So that brings us into chapter 4. Okay, chapter 4 is all about the idea that, okay, these molecules are not fixed in space. If I have a sigma bond, I can get rotation. Now, there is a slight barrier to rotation based on which groups you have, okay? And the way we looked at this is by drawing those Newman projections, okay? The Newman projection, make sure that you know how to draw the Newman projection where it's the sticks in the front are the front carbon that you're looking down the axis. The ring in the back is the back carbon, and then the things coming off the ring are the whatever's attached to that back carbon. We only go down 2 atoms, okay? So we're looking down a carbon-carbon bond and looking at what's attached to it. The beauty of the Newman projection is that we now see why there's the barrier to rotation. Because when we started with our completely staggered configuration where everybody's spread out as far as possible, we knew that was a lower energy conformation, because as our hydrogens start to butt up against each other in space, we can see that that's going to cause a little bit of distortion, a little bit of tension in that bond, and that's why it's higher energy. So there's a penalty for rotation, but if you have enough heat, you can do this rotation. Then of course, if you have the same substituents, you'll just have going back and forth, okay? So, but that changes when we add another group, okay? When we add another group that is bigger than hydrogen, now we have to pay attention to where those groups lie, okay? So let's pull that up right here. So in our starting point, what we do is we have it where our 2 groups, in this case, our 2 methyl groups in butane, are in what we call the anti-configuration. They are completely opposite each other. They are far away as possible, 180 degrees apart, okay? So that's our anti-configuration. And because they're as far apart as possible, that has to be our lowest energy conformation, okay? Now, by doing our rotation, we're now gonna start to see a carbon hydrogen eclipse, a carbon hydrogen eclipse, and a hydrogen hydrogen eclipse, okay? So this is gonna add more energy than these. And so we see that rise in that potential energy, okay? When we continue to rotate such that we now have the 2 methyl groups next to each other, but they're still not eclipsed, we have another term for that. It's called gauche, okay? Gauche is not as stable as the anti because they're still kind of close together. They can still see each other. And that's why it doesn't go to 0 in that gauche configuration. And then our highest energy is when we have two carbon-carbon interactions. That's our highest energy barrier for this particular thing. And when we have 2 large groups on there. And then we go to the opposite gauche configuration. We eclipse again, where we only have a carbon-hydrogen, carbon-hydrogen. And then we get to our anti-configuration at the end, okay? So the Newman projection gives us a visual idea of what's impinging on what is getting close to the other things. When you get 2 groups close to each other, that changes the potential energy of the molecule. All right. All right, which brought us to cyclohexanes. And again, cyclohexane is one of those magical things in the fact that because we can get it into a configuration where all of the atoms are in a staggered configuration and they're all at 109.5 degrees, that means that it has no ring strain when it's in that chair configuration. Okay. And if we were to convert from one chair configuration, oops, that's not on, no. From one chair configuration into the other chair configuration, we have to go through all these other high energy steps. But with enough heat, you can flip these chairs back and forth, okay? So let's talk about that in the presence of a Newman projection. Okay, I said in that chair position, we have a completely staggered set, right? And the only gauge interaction we have are the two carbons right here, and they're kind of fixed in space right there. And so that is our only kind of interaction they have. Everything else is staggered. Everything else is 109.5 degrees. Okay. So by converting our cyclohexane to our Newman projection here, we can see why this configuration is so stable. Okay. Now, in this configuration here, we got to remember there's two types of hydrogens. All the hydrogens that are in parallel to each other right here are called the axial hydrogens. Okay, actually, I'm going to put that in blue. All of the ones, notice that all of these hydrogens are parallel to each other. Those are axial. And those have a certain importance because you want the smallest groups to be in those axial positions if at all possible. All the other groups that are around the outside of the material are the equatorial ones. Okay. So if we flip from that to the boat, let's look at that configuration on the boat here. If we look at the Newman projection, we have all of our materials are eclipsed, except for the hydrogens that are sticking out down here. All the other ones are eclipsed. And because they're eclipsed, that's a higher energy configuration. So we were looking down these two bonds. Let's see, looking at 1 and 2. Yeah, we're looking down these bonds in this direction here, and this bond down that direction there. It's an I, not an arrow, sorry. And we can see that those are why we have that configuration. Actually, the Newman projection is upside down. But, okay. So that's why the boat configuration is not as, and it's the joy of the Newman projection that allows us to see that. Okay. So one of the other important aspects of the cyclohexane is when you go from chair 1 to the opposite chair, and you go through all those flipping right here, all of your axial things become equatorial, and all your equatorial things become axial. Okay. So that means by looking at which group and how many groups you have on your cyclohexane, you can tell what the preferred configuration will be, because your largest group or your largest number of large groups are going to be in the equatorial position. And that goes by size. Chlorine is not quite as big as a methyl group, and so it only spends 83% of its time in that equatorial position. It spends the other 17% of its time in that axial position. But methyl is bigger, and by the time we get to the T-butyl group, that's very large, very bulky. It spends 99.9% of its time in that equatorial position. Okay. And that is what we have for cyclohexanes. Okay. Now remember in the lecture, I showed you how to draw cyclohexanes, just so that you have it for your scratch paper. You know, you just do 2 parallel lines right here, and then 2 parallel lines here, and then 2 parallel lines there. And then you start adding your stuff. It helps to most of the time to add your axials first, and then sprinkle your equatorials out around. Okay. Questions on any chapter, 1 through 4. The exam is over 1 through 4, and 1 through 4 only. Your homework is due Friday, and you can use it as a review after. And this is your opportunity to ask questions.
The functional groups and like the list chart for nomenclature, are we gonna get that, or do we actually have to memorize like a carbon double bonded to an oxygen and then continued on?
You need to know these, yeah. You need to know these. You'll use them all semester, all this semester and all next semester. So yes, you need to know these. When I first did it, it was, you know, flashcards, and then you start seeing, when you see them enough, they start getting very familiar. But yes, you need to know these. And I did the flashcards when I did it, where I did it the general structure, and then I also did there it is. I did the general structure with just the R group, and then I actually drew real compounds like these, so that I would be able to draw the thing. Can you do another example of how to draw a Newman projection? Yes. Okay, so when we draw that Newman projection, it's all about having perspective, okay? So let's say we're gonna draw the Newman projection for this compound here, okay? And the first thing we have to do is we have to pick which of the things we're going to look down, okay? Actually, let me go ahead and take this last carbon off. Let me draw it like 1, 2, 3, 4. All right. And so we're going to pick which one we want to draw. And so we're going to pick this bond right here. So we're going to draw from this direction here. And I'm going to look at this molecule from this direction here. And let me make this a wedge coming out of this. And so from this perspective, I need to start with this carbon here in the front, okay? So I'm going to start with this blue carbon in the front first, and I'm going to draw 3 lines and put the substituents on here. I have this one right here, and so now that I'm looking at it that way, this one's sticking out of the plane, so it's going to be on my left side, so I'm going to put that on the left. So this is a CH3 group. This one's sticking up, and so that's in the plane. That's the CH3 group. And the last one, since it's not there, set, it must be a hydrogen. Okay. So now I'm going to look at the next carbon down here. This is a the green one. We're going to draw a ring around to represent that back carbon. And this methyl group is in the plane of the thing. So we're going to put the methyl group down here. And then the other 2 are not shown, so they must be hydrogens. And we draw it that way. Okay. So the first thing you do is have to pick which carbons you're going to look down, find out which direction you're going to look, and then when you do that, make sure that the things sticking out are on one side, the things that are in the plane are sticking up or down, and fill in everything else. Does that help? Okay. All right. So what I'll do now is, since this is the interview, I'm going to go ahead and stop recording, and you can ask questions freely. So let me stop recording.